Welcome to this brief presentation of the new line of combined instruments developed by Expert System Solutions to make available all the functions of two equipments of the Misura family with a limited investment. Thanks to this line of instruments, it is possible to get two of the analytical functions most needed in many laboratories: horizontal optical dilatometer together with the heating microscope, horizontal optical dilatometer together with the optical fleximeter, optical fleximeter together with the heating microscope. All the combined instruments look alike the normal single ones. They are available with the same options: two kilns with maximum temperature of 1200 or 1400 degrees centigrade and a maximum heating rate of 30 degrees per minute. The horizontal optical dilatometer combined with the heating microscope look alike the normal horizontal optical dilatometer. There is a large optical stage enclosed in a black anodized aluminium cage and a yellow furnace. The external differences are not quite obvious, but they are very important. For example, the light box contains three light sources, two lateral and one in the middle, which automatically switch on depending on the software selection. The optical bench contains three digital cameras which spot different points into the furnace. There are three optical paths between the furnace and the optical bench. This instrument is able to work as optical dilatometer thanks to the two lights on the sides. In this case, the specimen is 50 mm long and it is placed horizontally on the sample holder. The instrument can work as well as a heating microscope thanks to the central light source. In this case, the sample is shaped from pressed powder in the form of a cylinder 3 mm high and 2 mm in diameter. This instrument finds an ideal application in all the circumstances where it is important to know the softening behavior and the thermal expansion behavior of the material to be tested. One typical application is the quality control of the ceramic frits, where these information are technologically very important. Knowing the glass transition temperature, the temperature of dilatometric softening, and the half sphere point, it becomes possible to calculate the viscosity of the glass as a function of temperature, using the Vogel-Fultner-Tamm equation, the well-known VFT equation. The instrument which combines the horizontal optical dilatometer with the optical fleximeter looks exactly alike the previous one, but with a red furnace. Also here there are three optical paths. The two lateral beams are used for the non-contact thermal expansion tests, while the central beam is used for the optical fleximeter test. This instrument is very useful when it is important to know the thermal expansion and deflection upon heating. A typical application is the analysis of the thermal expansion mismatch between the glaze and the body in glaze articles like pottery or tiles. With this instrument it becomes possible to carry out the thermal expansion test and also the classical Steger test, which allows to identify the coupling temperature between the glaze and the body. This graph shows the thermal expansion of a wall tile body and of its glaze. This is the result of the deflection test performed on the glazed sample after the firing. The test is carried out up to the temperature high enough to melt the glaze. Then the test is followed also in the cooling. In the section of the curve recorded during the cooling, it is clearly identified a sharp change in slope. This temperature corresponds to the hardening point of the glaze. The glaze becomes stiff enough to start to develop a compressive stress which makes the body to bend downward. Overlapping the thermal expansion results and the deflection result, we get this graph, which is not quite clear yet. In order to obtain the final result, it is necessary to shift the thermal expansion curve of the glaze in order to overlap exactly the curve of the glaze and the curve of the body in correspondence of the temperature shown on the deflection test, in this case 700 degrees. This is the result of the shift. Now the thermal expansion curve of the body and of the glaze coincide at the coupling temperature. This is indeed what it is happening in the kiln. During the cooling, the glaze is able to follow the thermal contraction of the body as long as it is still liquid. When the temperature reaches a value low enough, the glaze becomes rigid and it is not able to follow the thermal contraction of the body. From this point on, the thermal expansion mismatch between the two materials will start to develop a stress. The two shifted thermal expansion curves do not coincide at the origin point anymore. The difference between the origin point of the two curves is proportional to the stress developed between the glaze and the body. The instrument which combines the optical fleximeter and the heating microscope is able to carry out flexion test and softening test. It looks similar to the optical fleximeter, with only one light source, but with an orange furnace. Nevertheless, the optical bench carries two digital cameras with a completely different optical system. One has a resolution of 0.5 micron and it is used for the flexion test. The other has a resolution of 100 micron and it is used for the heating microscope. Both the optical path spot the central area of the kiln, but in different positions. The fleximeter spots under the specimen, while the heating microscope spots above the sample holder. Other typical applications of the optical fleximeter are the pyroplastic deformation of sintered bodies and the study of the deformation caused by the water absorption on green material. The graph shown is the result of a pyroplasticity test on a double-layer technical porcelain specimen. This instrument can work as heating microscope as well, with the same function of the other models. Here following there is the result of a test on a swelling material. The images captured during the heating cycle can be transformed in a sequence, which can be seen as a movie. These movies can be compressed using standard video codec and they can be easily delivered by email.